Hello, and welcome back to the third episode of the Inference Talk. So this is the outline that you've seen before, and if you remember the last episode, we were looking at the voxel-wise inference and cluster-wise inference, looking at different ways in which you can quantify your surprise at a given statistic, provided that the null hypothesis is true. So what I'm going to talk about now is parametric versus non-parametric tests. First of all, what is a parametric test? Well, what we mean by that is that we are able, there's some sort of expression that allows us to calculate the null distribution easily. And obviously, so have you seen, that's very, very handy because that gives us a tool by which to calculate the p-value or the probability of obtaining a given statistic or higher, provided the null hypothesis is true. But most distributions are not that simple, if you remember these distributions. So this is the maximum statistic distribution, and this is the maximum cluster size distribution. They are not that easy, and as I said, there is no exact closed form expression for them. Besides, these closed form expressions, they tend to be available only when errors are normally distributed, and errors aren't always normally distributed. So I'll just show you one very, very striking example of when errors are not normally distributed, and that is a VBM style analysis. So hopefully you've already seen the talk about VBM analysis. So in that case, well, you know that the response variable is is for a given voxel, whether that is grey matter or not grey matter. So voxels tend to have either a value of 1 indicating they are grey matter, or a value of 0 indicating they're not grey matter, i.e. they are something else. So what we have here, we have two groups, students, train spotters, and we calculate the mean of each group, and that's fine. And we find that in this particular voxel we're looking at, 4 out of 10 in group number 1 is grey matter, 6 out of 10 in group number 2 is grey matter. That's fine, but the error or the deviation between the fitted mean and our data is anything but normally distributed, because essentially what it is value of either 0 or 1, and from that we subtract these means. Now this is a slight simplification, obviously, because there's also a Jacobian modulation in here, and so it's not quite as bad as this, but errors aren't always normally distributed. Right. So this is the max Z statistic and the max size statistics. Now there are approximations to these, and in particular there are approximations to this tail, sort of the far end tail of these distributions. And the reality is that that is only where we are interested in them, because that's what allows us to estimate a reasonable p-value for a p-value of 0.05, for example. We're not particularly interested in this part. But in order to get these approximations, some of the most complicated maths ever used in imaging had to be devised. And note, these approximations are still just valid under certain sets of assumptions, and importantly, we still need normal distributed errors. And also, if you then try and apply one of these approximations, outside of that set of assumptions, you might end up not controlling for type 1 errors particularly well at all. So there are many potential problems with them. Now, so these parametrics, so they're based on something called Gaussian random field theory. They were developed largely in, I would say, the 90s, and in particular Keith Worsley did an enormous amount of work in this, and a very, very, very impressive body of work. And they served us fantastically well at the time when we had little choice. And the reason we had little choice was that 20 years ago, 30 years ago, the computers just weren't as fast as they are today. So the non-parametric tests, the randomization tests that we today are able to do, because the computers are so fast, they really weren't practical at the time. But I would claim this very strongly, the future is non-parametric. So if you want to join us to this journey into the future, it's actually really, really easy. All you need to do is to change this from mixed effects flame in the feed GUI to randomize, and you're on your way to the future. So randomize, what this is something called permutation testing, where there's some permutation tests. So let's look at what permutation testing is. So simple permutation test. We have performed an experiment. We have two groups, group number 1 and group number 2. Now, if we calculate the statistics, so in this case, we calculated the different, statistic here, the t-statistic is 2.27. Now, if the null hypothesis is true, if the null hypothesis truly is true, then there is no difference between the groups. That's the definition of the null hypothesis. And that means we should be able to relabel the individual points without changing anything, i.e. if there's no difference between these two groups, I should be able to take a point from here and put it over here, or take a point from here and put it over here. And it really shouldn't change anything, because under the null hypothesis, these two groups are identical. So let me do this. So the original configuration into group 1 and group 2 gave us a t-value of 2.27. I'm now going to start doing this relabeling. So you see here I've moved 2 points from group 1 to group 2 and vice versa. And I calculate the t-value again. This time I got a t-value of 0.67. So let's just keep doing this and let's start collecting them. Different relabelings. You see this is a new relabeling. Got a t-value of 1.97. And let's keep doing this. And I do this 5,000 times, right? Now, if the null hypothesis truly were true, such that there were no difference between these two groups, we would expect the original t-value to just end up somewhere in the middle of this distribution, because there would be nothing special about the original configuration compared to all the other configuration if the null hypothesis was true. But what we're seeing in this case is that actually out of these 5,000 relabelings, there was only 90 of them that had a t-value equal or greater than 2.27. So that is roughly 1.8%, i.e. 90 over 5,000. So there's only a 1.8% chance of attaining a value greater than 2.27 if there is no difference between the groups. And this, as you see, this is just the same as the p-value we've seen before. We're just counting the number of cases that are as high as the original label or higher, and that gives us a p-value. And if we want to find the threshold for the 0.05 level, we simply find the 250th largest value, because 250 over 5,000 is 0.05, and it will be there somewhere. So it will be very easy to do this. So you can see what we've done here is we have used the data itself to build our own null distribution. And note that this is very different. So these simulations I've shown you before, where we have sort of pretended that we've been able to redo the experiment over and over and over again, these have been simulations. I've simulated the data. Now, that's actually, if you want to do this in practice, it's actually really problematic. And the reason it's problematic is there's so many sort of dependencies in the data, and if you don't get them absolutely right, that simulation is not going to get you the right result. But here we haven't simulated any data at all. We have taken the existing data and we've only changed the labelings around, so all these dependencies are there and they are correct. So this is a safe way, and make no mistake, it's very different to the simulation route. Right. And importantly, we can do this for any statistic, right? So you remember, this we're going to now look at the maximum set statistic again. And you remember that was, we had no, had a complicated distribution. We had no closed form for calculating this distribution, but we can calculate it. Now, if we can calculate a statistic, we can trivially use non-parametric inference on it. And now compare that to how complicated it is, if at all possible, to do it analytically. Okay, so imagine we have this case. We compare an activation by painful stimuli in two groups of 5 subjects each. And this is what we got. We got this activation here. It's in an area which we're really interested in. We have a t-value of 4.65. That looks very promising, but can we trust it? And in order to find out if we can trust it, what we do, so we simply do the same thing as we did in the univariate example now. So this was the original model, group 1, group 2, the second level model. We have a group difference map, and we found a maximum t-statistic, i.e. the highest t-statistic anywhere in the image was 4.65. And now we start permuting these labels. So here's the first permutation, and we have the maximum t-statistic somewhere else, and it's now 8.23. And is now 5.43, and each time we do this, relabeling, we save away this maximum t-statistic 5.84, and we keep doing this until we have done 5,000 permutations. Just a random, well, sort of an arbitrary number, 5,000 permutations, and we find that our original labeling wasn't anything special at all. If indeed the null hypothesis was true, we would expect to find the original labeling somewhere in the middle of this distribution, and that's exactly what we do. It was actually almost 4,000 permutations and yielded a higher maximum t-value than the original labeling, so we can't reject the null hypothesis in this case. Whereas, obviously, if the original labeling had been over here somewhere, we had been able to reject the null hypothesis. So you can see that this really complicated statistic, the maximum Z statistic, and remember it was the maximum Z statistic that allowed us to control the family-wise error. So this really complicated statistic, we have now trivially calculated the null distribution for it, or the distribution for it, and we've been able to say that in this particular case we could not reject the null hypothesis. Now, it all sounds very simple, and it is very, very simple, but there's one thing you need to be aware of, and that is something called exchangeability. So when we swap the labels on two data points, we need to make sure that they're exchangeable. So what do we mean by that? Well, we'll start to explain it by a case where it is not exchangeable, and that is first level FMRI. But before we go into that, we need to learn about covariance matrices. So you see a graph here, and it's just the height and weight. So it's a random sample of Swedish men. I've taken the height and weight of them, and we can see that we have some dispersion, some uncertainty in height. We have some dispersion in weight, and there seems to be some sort of correlation between them, which isn't surprising. Taller men tend to be heavier, and this is an example of a bivariate distribution. So this data sample is characterized by two means. It's the mean height and the mean weight, and a covariance matrix. So this is the variance of the height, and this is the variance of the weight. And what we have here is the covariance. And the fact that we have a positive number here means that the two variables vary, they co-vary positively, i.e. when one is larger, the other one tends to be larger as well. And another way of saying this is that we can say that if we know the height, let's say if we know where we are here, we can already say something about the weight. I mean, if we have no idea what the height is, well, then the uncertainty of the weight is the full uncertainty. But if we already know what the height is, let's say we know that it's 190 centimeters, well, then the uncertainty in the weight is already a lot smaller than if we didn't know the height. So you could say that by knowing the height, the observation of the weight is now worth less, i.e. there is less surprise left for us in that observation. And this is not limited to bivariate distributions. So here's just an example of a trivariate distribution where I've added the blood pressure as well. And now the covariance matrix is a 3x3 matrix with height, weight, and blood pressure. And we can see how they are covary in different ways here. This is the same data set as before, the same covariance matrix as before, and I just want to show you as an alternative way of visualizing the covariance matrix, because this is what we're going to use in the remaining, or in some of the remaining slices. Right, so let's now go to the example where we don't have exchangeability. And that example is first level FMRI data. So if you remember this slide from the GLM talk, so we had the data, we had the design matrix, we had the regression parameters, and we also have the Gaussian noise. And this time we're going to look more closely at this part. And what we have here is our description, or our sort of formal description of this noise vector here. And we're saying it's normal distributed with a zero mean and a covariance matrix, as denoted by a sigma here. Right, so first level FMRI data. So if you remember from the GLM talk, I was talking about how individual, or how the different data points in an FMRI data set are not independent. And the example I used was weather, where weather changes gradually over time. So if you want to have independent measurements, you need to let enough time pass between your individual measurements for them to be independent. And if we look at the bold signal, how the bold signal evolves in the brain, we can see that it evolves gradually and smoothly over time, right? And this is because the noise in bold data is mediated through the flow of blood so smooth. Now, if we take something like this, and then we sample it on every 20 seconds. So I have this continuous process, the bold signal in the brain, and I take a sample every 20 seconds. And now it no longer looks smooth. It no longer looks smooth. And that's because I've sampled it at something like its natural time scale. So I now have more or less independent measurements. And if I look at the variance-covariance matrix of this data, so what we have here is we have the variance at the first point, and then we have the variance at the second point, and this is simply the variance over all voxels. And then we can look at the covariance between points 1 and point 2, and we can see there is no covariance, there's no correlation between those points, they are independent. But we rarely measure bold signal every 20 seconds, a more typical TR would be something like every 3 seconds. And now you can see if we take a measurement every 3 seconds, we are back, so we are now sort of representing this original smooth time series. And if we look at the covariance matrix of this, so we can now see we have the same variance at point 1, the same variance at point 2, but now we have a positive covariance between points 1 and 2, we have a positive covariance between points 2 and 3, etc. And what that means is that given knowledge of point 1, we can make a fairly good guess of what is going to be in point 2. And that means that point 2 is now worth less than it would have been if we had had no information or no knowledge about point 1. So this is the reason why we need to correct for this. But it also means that, yeah, I'll show you in a second what it means. Right. So let's go back to exchangeability. So this is our model again. Now the model consists of our regressors and the noise model. Noise model describes this. Now all permutations, when we start permuting the rows of the design matrix here, all those permutations must result in equivalent models, right? And by equivalent, it means that this has to be preserved. So let's now see what happens if we swap two data points, for example, data point 5 and data point 10 here. So what happens now is we have introduced new covariances, right? So now we have a covariance between point 10 and points 4 and 6. So this covariance matrix is no longer equivalent to the covariance matrix we saw before. And for a random permutation, all of these covariances have just sort of been randomly scattered in the covariance matrix. So the models are no longer equivalent, and this is my first level FMRI data is not exchangeable. Right, so I hope this has explained a little bit what exchangeability is. So back to exchangeability. Data points are not exchangeable if swapping them means that the noise covariance matrix ends up looking different. And formally what we say is that the joint distribution of the data must be unchanged by the permutations under the null hypothesis, and that's essentially just the same thing as I'm saying up here. And as soon as the noise covariance matrix has non-zero off-diagonal elements, i.e. covariance in there, you need to be careful. I mean, it doesn't necessarily mean that you don't have exchangeability, but that's when you need to start thinking, right? Now, and this is important as well, you typically never estimate or see the covariance matrix, right? You know, you've probably done FMRI analysis in the past, but you've never seen that covariance matrix I've shown you. So what we need to do is we need to imagine it. We need to think about when we are deciding, can we use permutation testing? We need to think about what might the covariance matrix look like. And when you think about it, you think, oh, okay, so there's a covariance between that point and that point. That's when you might have a problem, right? Okay, so that was an example of data that wasn't exchangeable. So let's look at examples of data where we have exchangeability. So one example of that is two groups unpaired. So essentially what we have 10 data points, 5 belongs to group 1, 5 belongs to group 2, and this is the model, calculating the mean for group 1 and calculates the mean for group 2, right? And here is the exchangeability group, right? So essentially what we said here is that these all belong to the one and the same group. So we can exchange labels and data freely in this entire group here. Right. Now, one thing you need to be aware of is that this group labeling, unfortunately, is used for completely different purposes in flame Gaussian random field theory. So it might be a little bit confusing, but just remember, in randomization testing, or when using randomize, what it means that we can exchange within this group. Right, and the implicit assumption here that allows us to do this exchange, that allows us to do this exchanging, is that data from all subjects have the same uncertainty and they're all independent. Right. Now, if the experiments are done in the same way, and it's reasonable to assume that the uncertainty is the same for all of them, and there's absolutely no reason to believe that subject 1 would be in any way covariant with subject 2, because they are completely unrelated subjects. So it's a reasonable assumption. Right, so two groups unpaired. Just look at what's happening. So the original labeling is 1, 2, 3, 4, 5, and then 6, 7, 8, 9. And then what we're doing is we're just permuting this. So first permutation might be that we have changed like this. So now, in what is now in the first group is subject 6, 3, 7, 8, and 5. And what's now group number 2 is subjects 1, 2, 4, 9, and 10. Permutation 2, again, we've swapped things around. We need to be aware that there are permutations that are equivalent. So permutation 3 is not identical to permutation 2, but you have the same subjects in the first group as you have in permutation 2, and you have the same subjects in the second group as you have in permutation 2. So permutation 3 is equivalent to permutation 2, so this is a non-allowed permutation. But this is something that randomize will take care of for you, so it will only do the allowed ones. So this was one example of exchangeability, two groups unpaired, no problems at all, right? Now we have a different one, a single group average. And what we're doing here is essentially we have done first level analysis on 10 subjects, and we now want to see, is there any average activation across these subjects, i.e. we want to know if the mean is different from 0. So now we just have a single group and a single mean, and we want to know if that is different from 0. We have the exchangeability group here, so it's completely exchangeable, but there isn't really anything to permute now, or is there? Well, just as before, if you remember before, we said that if the null hypothesis is, if you have two groups and the null hypothesis is true, right, we can just swap the labels between these two groups, because the two groups doesn't actually mean anything if the null hypothesis is true. Now, similarly, if the null hypothesis, which in this case is that the mean is 0, if that null hypothesis is true, then all these values are just random variations around 0. And then if they are just random variations around 0, it shouldn't matter if we take the value or if we take the negation of the value. So the original labeling, let's just be taking the values all as they are, we get a certain t-value. But then the first flip, we just randomly sign flipped some of the values. And the second flip, and the third flip, etc. So again, we build up this null distribution. In this case, it turns out that this was completely insignificant, right? But we can do the same trick as before, just by doing this sign swapping. And the assumptions here is symmetric errors, errors independent, and subjects drawn from a single population. So, another example of exchangeability is if we have two groups paired. But now the exchangeability is restricted, right? So two groups paired. So what we have here is we have two conditions. So each and every one of 5 subjects have been scanned in condition A and condition B. And the first EV just looks at the difference between the two conditions, and EVs number 2, 3, 4, 5 and 6 are simply the subject-specific EVs. And I'm sure you have seen this now before in MJ's previous talks, so that you understand what these are. Now, if we now look at the group variable here, we see that now we have exchangeability only within the first subject, and only within the second subject, and only within the third subject. So, what are the assumptions for this? Well, the implicit assumptions here is that data from all subjects have the same uncertainty, and there is no dependence between subjects, right? And if there's no dependence between subjects, this is what the variance-covariance matrix is going to look like. And if I swap these two, i.e. condition A and condition B, in subject number 2, I'm not going to change anything. Right? So the variance-covariance matrix is going to be exactly the same as before. So this is an allowed swap. But if I go and swap condition A to condition B between subject 2 and subject 4, we completely change the covariance structure. So this is not an allowed swap. Right. And what we're doing here when we're doing the permutations, so this is just an example. So again, remember, we can only swap within subjects. So the original is 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7 of the scans here. And the first permutation, then we just swap positions in the first subject. We have retained the position in the second subject and the third subject. We swap positions in the fourth subject and we retain positions in the fifth subject. And then we can go on like this, but only swapping within subject. Right. Now, blocked ANOVA, again, I'm sure this is something that you've seen in the previous talk. And now what we have is we have 5 subjects. Each of these subjects have been scanned in 3 conditions. And the first EV is the contrast between conditions A and B, and the second EV is the contrast, the difference between conditions B and C. And then you have the sort of the block EVs for subjects 1 to 5. And same as before, if you look at the group variable here, we can now only swap labels within each subject. So within subject 1, we can swap the labels freely. Within subject 2, we can swap the labels freely. Within subject 3, we can swap the labels freely. And what are the assumptions that allow us to do this now? Well, the assumptions now is that all subjects come from the same population. There's no dependence between the subjects. And we have compound symmetry within subjects. Now, I think the first 2 assumptions here, all subjects from the same population, fine. no dependence between subjects. There's clearly no dependence between subjects. The compound symmetry one, that's a little bit trickier. And what compound symmetry means is that within each of these blocks constituting one subject, all of the off-diagonal covariances are identical. So if this is true, i.e. all of these variables here or all of these covariances are identical, then we can swap freely. We can swap condition A and condition C within subject 2 here. But if we don't have compound symmetry, i.e. if there are slight differences in covariance, this is no longer an allowed swap, because see what happens when I do that swap. It's subtle, so I'm going to go back and forth with it a couple of times, but you can see that this actually changes when we swap it. So compound symmetry is as a prerequisite for exchangeability in block de novas, and it's something that it's not completely obvious that is true. So my advice for doing these things is keep it simple, and there's almost always a way to keep it simple. So actually you don't need to have these complicated blocked models at the second level. So I'm going to sort of exemplify this by this study here. So what we have is we have a study where at the first level we have painful stimuli at 4 different levels. So we have a little pain, we have more pain, we have even more pain, and we have, ouch, bad pain. And what we want to do is we want to find areas that respond linearly to pain. Now there are 2 different ways that we can take data like this to the second level. The first example, the first way that we can do this is by taking 4 contrasts from each subject to the second level, and those contrasts is simply the individual conditions. So we're taking the little pain condition, the more pain condition, loss of pain condition, and the ouch as 4 images for these subjects to the second level. So, and we're then repeating this for 4 subjects. So we have 4 conditions, we have 4 subjects, and we are ending up with a design matrix like this. And if you now, so this first EV at the second level model contrasts a little bit more pain to little pain, and the second one contrasts lots of pain to more pain, and the third one contrasts lots and lots of pain to lots of pain, and then we have the block EVs. Right, now if you want to do randomize on this, what you have to do is you have to assume this covariance matrix, i.e. compound symmetry, because if you don't have compound symmetry, you can't do randomization on this. And in addition to that, you also have to figure out this contrast, which is, it's not that hard, but at least you have to sit down and figure out, okay, what does the contrast look like that gives me a linear response to pain? So why put yourself through all that complication, all that pain, when you can keep it much more simple? And the way to keep it much more simple is to take a single contrast per subject from the first level, because we are interested in the linear response to pain. So we are entering the linear contrast to pain at the first level, and we're taking now only a single image per subject to the second level. So now the second level model looks like this. And if you remember, when you have a single mean that you're interested in, what you're doing then is you're doing the sign swapping, i.e. you are doing the negation or the non-negation of the different labels. And that assumes only symmetric errors. So what you have now is you have a much, much simpler contrast, and you have much less stringent assumptions. Much nicer now. So my advice is that whenever, and you pretty much can always do this, right? Set up the complicated contrast you're interested in at the first level, and then take something very simple to the second level, so that you end up with a model like this, or at worst 2 groups in the model. And you can pretty much do this always, and then the assumptions regarding exchangeability are pretty much always true. Right, this is just a warning. I'm guessing no one is using random FSL 6.0.1 anymore, but there was a bug in FSL 6.0.1, which means that you should not use the model setup wizard together with randomize in that particular version of FSL. Just a little warning, and I hope that's fine. Okay, so this was episode 3 of the inference talk, and next time what we're going to do is we're going to talk about enhanced clusters and false discovery rate, but in order to see this you will have to tune in to episode 4 of the inference talk. Thank you very much.